We have a really big water tower, really high water tower, 360 or 120 meters, pushing 400 feet. Probably don't want to build one that big. It gets really hard to withstand the pressure at the bottom. In any case, we're going to take this thing, fill it to 120 meters, and then we're going to pump more water into it so that the water level rises to 120.34 meters. So I'm going to draw that level in a different color, and I'm going to kind of shade that region in so we see the water that was added. Now this isn't to scale. 0.34 meters on the scale from 0 to 120 here would be a very thin layer. So I'm exaggerating the thickness of this layer still. Now my question is, how much did the potential energy change when we pump this in? Potential energy relative to the 0 meter position, if we wish, because in a minute we're going to open a valve down here and let the water flow out at this point. So that the delta PE relative to 0 meter altitude is what? Well, we've got to have a cross-sectional area here. So I'm going to assume we have a uniform cross-sectional area, and I'm just going to say the cross-sectional area is ACS. It's actually going to turn out not to make any difference, but let's give the cross-sectional area. Let's do a symbol for the cross-sectional area so we can actually write down the potential energy change. So, the potential energy of this water relative to this is what? Well, the volume added is ACS times 0.34 meters. Now the mass, now let's just do the weight. What's the weight of the added water? Well, we multiply 1,000 kilograms per cubic meter, the density of water, times the cross-sectional area. And I mentioned we could have just used rho for the density here, the symbol, as you'll see in a few minutes. And then we multiply that times the 0.34 meters. That's the mass of the added water, because we've multiplied the density by the volume. And then we multiply that times 9.8 meters per second squared to get the weight of the added water. Okay, then the change in the potential energy of the system due to this, if we're assuming that we're pumping the water from here up to here so that later on we can return it from here down to here, the change in potential energy is going to be equal and opposite to the work done by conservative forces. The work done by the conservative force is gravity. The force exerted by gravity is the weight acting downward. The water is pumped upward, so that's equal to the negative of the conservative force multiplied by the change in altitude. The conservative force is downward, the delta y is upward. So let's take upward as positive, so that downward is negative. So that's negative of this. Now, I'm going to multiply these numbers out. 0.34 times 9.8 is about 3.3 times 1,000 is 3,300. So this is going to be 3,300 kilograms per meter cubed times meters per second squared. That's going to be kilograms over meters, excuse me, second squared. And gravity's acting down, so we're going to do that. We're going to make this negative, in other words. And then our delta y is approximately 120 meters. Now we could split hairs and say, well, you know, we should use 120.17, which is halfway between here and here, and we could argue that. But since I'm going to do most of the numbers pretty approximately, we'll stick with this. And then that's times, of course, our cross-sectional area. Now, let's see, 120 times 3,000 is 360,000, and 120 times 300 is 36,000. So I think we end up with 396,000. I think that's it. And that's going to be kilograms over second squared multiplied by cross-sectional area. So there's our change in potential area, not potential energy. Okay, now if we open a valve and let the water flow out, assuming it's an ideal fluid, no friction or anything, then by the time the water gets back down to here, the potential energy will have decreased by this much. Now, in this situation, remember the work energy idea, that the work done by non-conservative force is equal to the change in kinetic energy plus the change in potential energy. For an ideal fluid, the work done by the conservative force is 0, so change in kinetic energy is equal and opposite to the change in potential energy. Now this is a change in potential energy when we're pumping the water in. Pumping the water out, the change of potential energy will be opposite to this. So maybe I should put an N here. That's as water is going into the container, the vessel, the tower, whatever we want to call it. As it comes out, well, it's the change in kinetic, we're talking about the change in kinetic energy now from this position to where the water comes back down to here and exits down here. So we're going to have an equal amount of water exiting down here. So that water is going to be coming out of there. It's going to be coming out of there really fast too. So we can imagine the stream of water just continuing on. The change in the potential energy of the water as it comes out here, replacing the water that's lost up here, is going to be equal and opposite to the change of potential energy when we pump the water in. So that's going to equal negative 396,000 kilograms per second squared times cross-sectional area. Now, what is the change in potential energy? That's the change in kinetic energy. That's the 1/2 mVf squared. Now, making a little note here. The initial velocity of this fluid is 0. So the change in kinetic energy equals just the final kinetic energy, which is 1/2 mvf squared. So that's where this 1/2 mvf squared comes from, to just complete the idea. Okay, so now what's the mass? Well, we already calculated the mass of this fluid. It's this. Now I can multiply that out. I'm going to get 340 kilograms per cubic meter times ACS. Excuse me. But first, I think I'm going to want to do this. We're just going to say that since 1/2 mvf squared is a change in kinetic energy, and that's equal to the negative of the potential energy out, I'm going to say that Vf is plus or minus the square root of our 2 times our negative change in potential energy divided by the mass. Just doing the algebra to solve this equation. Okay, the change in potential energy, well, I wrote it in here. It's plus or minus the square root of 2 times negative 396,000 kilograms per second squared times the cross-sectional area divided by the mass. Well, the mass is right here. It's going to be 340. And it's kilograms per, yeah, I think I missed something in my units. No, never mind. Okay, kilograms per meter squared times ACS. Now, the kilograms per meter squared divide into the kilograms per second squared. Multiplying by the reciprocal, we see that we're going to get meters squared over seconds squared. Dividing this by this gives us meters squared over seconds squared. Kilograms divide out, meter goes up on top. The cross-sectional area divides out, and we simply end up with this into this. And that ends up being something like, okay, units of meters squared per second squared. 340 goes into 396 about 11.7 times, something like this. And that left off a negative sign. And I don't have room to insert it, so I'm just going to make that positive, being a little sloppy. The delta PE is negative. And then we have the negative of that, which gives us the positive here. I missed that. So anyhow, we're going to end up with something like 22,000. I'm going to just say about 23,000 meters squared per second squared, square root of that, and that's going to be approximately what, plus or minus 150 meters per second. Very close to that. Okay, so now we have the potential energy to increase, and then we have an equal potential energy decrease converted to kinetic energy, giving us 150 meter per second exit velocity.